Hi, this is the first of this week's videos for the Further Maths core. We're starting chapter 7, I'm in red, let's change that. Starting chapter 7, I'm just going to work through the examples to work towards exercise 7a. So we're looking at transformations using matrices. You know, the transformations that we did at GCSE, your enlargements and your stretching and all the rest of it. We can describe transformation using matrices. And this is how we do that. I've got this transformation, I'm going to call it S. It takes a pair of coordinates and it transforms it in this way. So it adds 4 to the x coordinate and subtracts 1 from the y coordinate. That's clearly a translation. Now if I want to apply a transformation to a point, 2, 3, then I can just say that 2, 3 gets sent to 6, 2. Or 2, 3 gets sent to 6, 2. I mean, that's straightforward enough, isn't it? Again, look at a different example, same deal. 2x minus y and x add y. So again, if I send 2, 3, that's going to go to 1, 5. 2 times x, 4 minus y, 3. And the third one sends xy to 2y minus x squared. So again, not rocket science. 2, 3 goes to 6 minus 4. And I can write it as vectors, but I actually want it as points. And remember, coordinates are written in brackets. Now these are all valid transformations, but we're only interested in a subset of transformations, in linear transformations. And a linear transformation is the only type of transformation that I can represent with a matrix. So a linear transformation can be represented with a matrix, let's call it A, B, C, D. And if I apply A, B, C, D to x, y, I get ax plus by, cx plus dy. So a linear transformation is the only type of transformation that I can, I'll say that differently. I can only represent a linear transformation with matrices. And a linear transformation in this definition will look like ax plus by, cx plus dy. So S is not linear because it doesn't look like this. T is linear because it looks like ax plus by, cx plus dy. And U is not linear. It doesn't look like ax plus by, cx plus dy. Now, generally, when we define these transformations with matrices, we give this matrix here rather than the product here. And we'll look at that in more detail in the next chapter. The other thing with a linear transformation is it must map the origin to the origin. It must map the origin to itself. If it doesn't do that, it is not a linear transformation. And again, you can see, you could just use your brain. If I apply S to 0, 0, I'm not going to get 0, 0. If I apply, so S is not linear. U, I can't represent as a bracket. T, if I apply t to 0, 0, well, 2 times 0 minus 0 is 0, and 0 plus 0 is 0. So t is also linear because if I put in 0, 0, it gets mapped to 0, 0. So when I'm defining my transformation, it needs to look like this. X and Y on the top, X and Y on the bottom. Example 2 simply says, write these matrices in the right form. So that was example 1. Example 2 just says, let's move my book. Write these how I want them. Well, I wouldn't write it like that. I'd write it like I have the x first and the y second, and I could have 3x plus 0y, but I won't bother. That's what I want to see. That's the matrix that I want to see. X first, y second. Actually, what I want to see is the matrix that represents it. 1, 2, 3, 0. That represents the transformation. Let's look at the second one. V sends xy to minus 2y, 3x, add y. Well, let's write it in the way that I want. 0x minus 2y, 3x, add y. So matrix V I'd write as 0, minus 2, 3, y. And if you think about it, that makes sense, because if I apply 0, minus 2, 3y to a general point xy, then I end up with what I want. 0x and minus 2y, 3x, oops, that should be 1, sorry, 3x and 1y, which is what I want. So this is the matrix that I want to see. That's what represents that linear transformation. Now, as I've suggested, to apply a transformation, you just multiply the 2 by 2 by the point. And example 3 just does that. It gives the transformation matrix as minus 1, 2, 2, 1, and then it applies it to 1, 1, 1, 3, no, 3, 1, 3, 3, and 1, 3. In the book, and I don't like the way they do this in the book, and I'm looking on page 128, they do all the multiplications separately. Now you can do that, and you get an image for each point. But what I'd rather, because it's quicker, is I can apply it to each one separately. So the book says, do minus 1, 2, 2, 1 to point 1, 1. And that gives me 1, 3. So 1, 1 maps to 1, 3. And then they say do each point separately. And that's fine. 3, 1 maps to minus 1, 7. I think a better way, a more efficient way, is to do them all at once. So I'm not going to use the strategy that the book comes up with, although of course it does work, and you're using your calculator to do these. I'm going to do all the points at once. So I still apply the matrix, the transformation matrix, but I apply it to all my points at once. 1, 1, 3, 1, 3, 3, and 1, 3. Now remember, this is a 2 by 2. this is a 2 by 4, so it works because the columns match. The columns matches the rows, and I'm going to end up with a 2 by 4. I'm going to end up with a 2 by 4 matrix that represents all the images at once. And using my calculator, I get 1 3 minus 1 7 3 9 5 5. So I can work on more than one point at once, and personally I prefer to do that. Let's be honest, I'm using my calculator to do it anyway, so why wouldn't I do that? And for part B that says to sketch, well, I'll sketch the quadrilateral given by these 4 points, and the image, there's a quadrilateral given by another 4 points. I'm not going to do that now because you know how to plot points, and also, of course, there's a picture of it in the book. So we could say that this matrix, minus 1, 2, 2, 1, represents, looks like some sort of enlargement. I don't know what it is because I haven't worked it out, but also I don't care what it is. Okay, so for 7A, we should be good to go. Let me know if you need anything, and I'll come up with the next video for the lesson on Friday. Okay, hope to see you soon. Hope you're all well. Bye-bye.